Okay, so welcome to another video, and here's the circuit for the bipolar commutation with, oh shoot, I still need to add the coil. That'll happen in a minute. With the coil and a cap, and this was the code we went over last time, so everything's about the same. I just, the only other thing is I put in a full wave bridge rectifier, and you can't have single diode rectification like a boost or a buck boost because you're going back and forth between positive and negative. So you want a full wave bridge rectifier, and that's what those four are. Be positive there, negative there, and those are your other two lines to the coil. I'm not even going to hook that up. I mean, the first thing is just, will it spin? As the commander of the Dallas said to Jack Ryan, there's still about a million things that can go wrong with this stunt, Ryan. They're charging Alec Baldwin with involuntary manslaughter for his accidental killing there of someone on a movie set. It was very tragic, very tragic. Maybe that's why I got one of his movies there in mind. So here's 12 volts, and this will be our power supply. There are just 3 lithium ions, about 4 volts each. And so let's just make sure that it's still doing what it should. Let me find the magnet here, and bring it past 12. Bring it past again. Discharges, goes to negative 12. So everything is working correct. And, so like right now we just have it, 2 seconds discharge, 1 second charge, so you can see what the heck's going on. So as I said, there's still like a lot of things that can go wrong. One of them is, these lines and the baud rate of 9600, is that going to be, I can go up on the baud rate. I don't know if there's any drawbacks to that, and I don't know if I need to go up on the baud rate. I still haven't replaced these digital writes, so they're going to take up a bit of extra time. But let's just see if like anything's happening before like trying to optimize it and put in the bridge rectifier and things like that. And it might not work with this, it might, but then here's one that's 10 times as big. If it's not going to spin with that, then there's probably something wrong. So let's see what it does. And then, in terms of these numbers, here you just want to fill the cap as quick as you can until it's fully filled. And for this number, you want it to be half of the resonant frequency. And so if we go back here to some earlier work with the small green coil, there's our inductance and resistance, the tau time, but what we're talking about here, the resonant frequency. So with the 10 UF, resonant frequency is 0.9424 milliseconds, so the optimal on time would be about 462 microseconds, right? Check. So I think this is let's see what happens. Okay, starting to take shape. So, and instantly there's a problem before even trying to get it off the ground. So now I've got this hooked up with it's discharging through the coil, and it only charges one way. Let me go the other way. Come on, go the other way. And it goes to negative a half volt instead of negative 12.3. How did that happen? So it can't be the battery connection from the battery because it charges to 12.3. It can't be the ground line. I mean, it can't be that because that's just discharging the coil, not when it's charging. I sure hope I didn't fry one of the Comus AC37s because I've got 10 more on order, but these are the last of them. I need to figure out why it's not charging the other way. So I'll get back to you. Somehow, even though I'm only at 12 volts, I managed to fry both channels on one of those relays. Now, because it charges up to 12 volts, I know that that channel has to be, both channels there have to be good. And because it discharges, that one's good. So I've got 10 more of these dual channel Comus AC37s on the way. They won't be here for a couple days. So I can scavenge from the test bed, and I have 3 of those where one channel is working. So if both channels are still working on this one, he's going to move over to the left tackle, and I'll use one of those one channels since we only need one and put him in center. And then it should run, and you know, we'll have warp drive. Okay, 12, negative 12. I don't want to get it too close to the rotor because I'm afraid I'll fry it again before I fix the timer. So it's working, and it's just charging through the coil. Okay, so as I was saying, this is really good. Now, before a few minutes ago, I was saying that the resonant frequency was 920 microseconds. I'm wrong. I already calculated the half resonant frequency. The half resonant frequency is 920 milliseconds. That's about what you want the pulse rate. So I just said, you know, like, screw it. Before we put in delay microseconds, let's just delay 1 millisecond. So delay 1,000 microseconds. You're not at the resonant frequency, but you're not at the half resonant frequency, but you're not way far off. And when you go to charge it, delay for 1 millisecond. That'll give plenty time to charge that from these batteries. And then there. And all I did was bring the thing in. I hope it still works. And it started making these Star Trek noises, and it started spinning. Boom, 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 boom. Holy crap-oly. This is good. This is from a 10 UF cap. And I haven't tried to get this positioning right. So the next thing, this is goddamn good. Sorry, Jesus. This is impressing myself. Sorry. Wow. I'm just saying that. Look at that air gap. Look at that little 10 UF. Now what we're going to do next is we're going to put, and we're not even fully in resonance. We're just like close. We're like ballparking the resonance, the half resonance. This is like when a plan comes together kind of thing. So now what we need to do, and let me pull this away before it might start stepping on its toes and shorting, blowing up one of those again. I don't think we're anywhere near that. That would be 2,000 RPMs. That was probably like 800, 500, 800. Now we need to put in an, I like to call it ammeter. I guess some people say ammeter. I don't know, maybe that's like French. So we need to put in an ammeter and see what are we actually drawing. And then, you know, we're going to go to delay microseconds. We're going to change this closer and further away from the half resonant point. We're going to observe the rotational speed, and we're going to observe the amp draw. And as I said, I didn't try and get that. I just literally just plunked this thing down here and brought that in. But there's going to be a sweet spot, you know, like there, or is it there? There's going to be a sweet spot there, or is it there, or is it there? And for maximal rotation. Okay, before we even put in the ammeter, let's check something else out first. So now I have changed this to delay microseconds to 1,000. I can go back to the spreadsheet, but from memory, the calculated 1/2 resonance is 924 microseconds. So that means right around, 1850, this thing just shouldn't run at all. I mean, because at the full resonance, the current here will go one way and then the other way before this thing has a chance to flip past. And it should just, if anything, go. And that's it. And then, as you get closer to 920, and then, we'll check on the spreadsheet exactly what it was. As you get closer to that half resonance is where you're only getting the one way. And furthermore, that's where you're gathering from the spring-like action of the cap the most of your voltage back, and that will show up on the ammeter. So in other words, when I bring this thing out of resonance, and it's not exactly in resonance now, but it's close. When I bring it out of resonance, it shouldn't spin, and it would draw more current if it spins at all. As we get closer to resonance, it'll start to spin, and the closer we get, it should spin faster and draw less current. So let's give that a try, and man, I hope this doesn't blow up, because this is actually getting exciting for me. Sorry. I'll contain myself. Okay, I am digging this. It actually does run at 1900, and I think the only reason that it runs is because when it reverses current, that's actually going to be slightly weaker because of the resistance. But it does run, and the other weird thing is the noise, and I put my ear up to it. The noise sounds like it's coming from the magnets, as silly as that sounds. But here it is at 1900, and then we'll put it back to... Okay. See, it doesn't want to do anything. I need to get this around. If you actually let it spin a little, so this is way out of resonance, and it does do something. And I think the only reason it does anything is because the pulse this way, and then with the resistance, the pulse the other way is a little bit weaker, and that's all you're running off. It's like the sound's coming from the magnets. I mean, I didn't expect the sound effects. Okay, let's put it back to 1000, which again is not entirely in resonance. And I'm going to try to leave that thing exactly where it is there. And then we'll do this again. Give me a minute. Okay, so now I've compiled it at 1000. Again, the resonance is going to be like 920, but a lot closer than 900. And you saw how it behaved before. Let me see if I can just bring this in. See, that's working a heck of a lot better. Wouldn't you say? Okay, we'll just let that go for a little bit, and then we're going to try and gather some data. And for heaven's sakes, you know, where's going to be the sweet spot? You want it out there? Whoops, you don't want it there. Okay, more to do. Okay, so now we're going to throw in an amp meter, and I just took the power supply here at 2.8 volts and put in a random resistor and connected them, and we're drawing 0.03 amps across there. So now we will put this meter in series with the circuit so that the amperage has to flow through the meter as well, and this meter should also register 30 milliwatts or thereabouts, hopefully a little more accurate. I've also managed to, I've fried the ammeter on there. One or two of these $20 cheap meters still has a functioning ammeter. And so I'm going to find out which it is, and that's what I'm doing now. Okay, so now, and I never remember whether to hook this one to the positive or the negative. So the positive goes to the positive here, through the meter to the negative, and then it'll go through the resistor to the negative of the power supply. Get on there. Sorry. There we go. And 27.2 milliamps, 0.03 amps. So this is still functioning. Okay, so in a moment we will hook up the amp meter and we will look at the amp draw in and out of resonance, and I'll also probably put an RPM meter and figure out what it's spinning at in and out of resonance, and I'll also be moving the coil around to different locations in terms of angles for the trigger. And I'm so happy it worked with that 10UF. That's just mind-blowing to me now. But to those who fiddle around with this, there be a little erudite discussion, of considering constant voltage versus a cap. You know, what am I getting at here? So give me a minute to think what I'm getting at. Okay, so let's say we have a constant voltage source and there's no timing involved except for when the magnet swings past, while the reed switch is shut, power flows. When the magnet gets far enough away, the reed switch separates, power stops flowing. Therefore, let me disconnect this. If you are going at that speed, you'll have a quarter second with it on, quarter second with it off, quarter second with it on, quarter second with it off. If you're going at that speed, you'll have a 100th second on, 100th second off. So what I'm saying is that the duty cycle will be determined by the spacing of these magnets and how far away your trigger is. If the trigger's in real close, then it's going to be on like 90% of the time and then just off. If it's very far away, I might just trigger it there and then it's off 90% of the time. But the duty cycle will be constant at 10 RPMs or at 10,000 RPMs. Right? Yes. Check. So what you see in a situation with constant voltage is as you spin the rotor faster, amp draw decreases. But why does it decrease? The duty cycle is constant. It's always going to be on, say, half the time, off half the time. It decreases because of the reactance of the coil. I've covered this ad nauseum in previous videos, that you have the transit curve, and initially there's a tremendous amount of resistance to the change in current. As you get towards saturation, there's less and less. When it's fully saturated, it's just pouring out current through the coil, establishing a constant magnetic field with only the direct DC resistance of the wire. But initially, there's a tremendous amount of reactive resistance lessening as you get to saturation. So as you spin faster with a constant voltage source, even though the duty cycle is the same, independent of RPMs, the amp draw decreases. We have a different situation here. Here you've just got this little 10 UF bucket, and you throw the 10 UF bucket out once, and then it takes a minute, and then you throw the 10 UF bucket out a second time. Or it's going at 60 RPMs, and you throw a 10 UF bucket, a 10 UF bucket, 10 UF bucket, or it's going at 6,000 RPMs, and 100 times a second you're throwing a 10 UF bucket. So in other words, the duty cycle is no longer constant, because once you've expended the 10 UF, there's nothing left to expend, and then it's just blank space. And you're always expending the 10 UF fully. So in other words, if you spin this at 100 RPMs and you expend 1 coulomb, and then you spin it at 1,000 RPMs, you would be expected to expend 10 coulombs, because there's going to be no change in the reactance. It's always just the same capacitor discharging into the coil, but it's going to happen 10 times as fast. So what I'm saying is that unlike with the constant DC voltage source, whereas you speed up, you would expect to see a decrease in amp draw because the duty cycle is constant and you're getting more reactant, you're getting greater reactance from the coil. With this setup, there should be, I would say, essentially a one-to-one relationship between how fast it's spinning and how much current you draw. So at 10 times as fast, you should draw 10 times as much current. So that's a different thing. So just so that we're all on the same page. Now also, you know, I've double checked this code and I'll triple check it. But I might not have built what I thought I built. You know, maybe somehow it's power from the battery or whatever. The thing that kind of bothers me is that long boop, 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 as it spins. And what the heck is that? Because that sounds like it would be coming from power. But you look at this and it says pin 11 high, then pin 11 low after 1,000 microseconds. You know, here's that's pin 11, this is pin 13. Those are the two. Wait a minute. Let's back up. Let me think. Yes, I had it right. Pin 11 is when you're... Pin 11 is when you are discharging this. So, you know, it's at 1,000 microseconds here. Goes through that. Pin 13 is when you just charge the cap and then you shut it off. Then pin 11 high, a certain number of microseconds. And then pin 12, you charge it the other way and then off. Only thing I don't know is what's with the sound effects, and why is there a when there's only a little boop from this. So that has me a little bit worried. But let's put in the amp meter, you know. I'm diddling around too much. Okay, I'm still not where I thought I was, and I'll show you why right now. That's why. See, we're drawing amperage there, and we shouldn't be. Let me disconnect it. Okay. And I need another toggle. That's what I've come up with. We're getting there, but we're not there. And so why do I say that? So this, it's like pin 11, the discharge. That goes high, and then it goes low, and then you charge it. And then it goes high and goes low the other way, and then you charge it the other way. And if the magnet is away, then you don't do anything. So why in the heck, when the magnet is there, just sitting there, does it keep going? And I'm realizing, these things, you have to tell them absolutely everything. So in other words, it goes through, and while the magnet's still there, it does a second pulse, and then it does a third pulse, and then it does a fourth pulse until it's finally out of there. And so it's getting closer, because you can now see a distinction between when you're in and out of resonance, that the pulse is better or worse. But you only want it to pulse once, even if you leave the thing sitting there. I'm going to have to go back to putting the magnet there. I'm still not sure how that is happening, but it is happening. It's charging up the cap and discharging it again when you just leave it there. I'm sorry. I'm so sorry. But I can at least demonstrate for you the distinction between in and out of resonance. So here we're out of resonance. Let's plug it back in. And you gotta admit it sounds pretty darn cool. Do something. Yeah, we'll let that spin up, and we're gonna look at the amp draw and the RPMs. Okay, so even with this thing, focus. It's not gonna focus. I don't care. Maybe over here? There we go. It's drawing 17.6 milliamps, and we're running at is that right? That can't be right. Give me a second. I don't think it's running at 409. That sounds too fast. Uh-oh. I guess that's right. So this is gonna stink. 413 RPMs. Okay, that's what we'll say. 400 RPMs, and when I knocked it there, it slowed down. It was at 18. Okay, we'll call it 400 RPMs and 17 milliamps. 400 RPMs, 17 milliamps. It was at 18. 400 RPMs, 18 milliamps. So you get 400 RPMs, what we measured, 18 milliamps. Okay, so now I just put it close to resonance at 940 RPMs. And, a bizarre thing is that as the RPMs are speeding up, this is not going up. And that can no longer be the reactance of the coil. That is timing rectification of the radiant. So let's let it spin up for a while. runs a heck of a lot better. Okay, so it's in resonance now. I moved the coil a little bit. We're drawing, instead of 17, we're drawing about 30, so a little less than double. And instead of at 400 RPMs, we're at 1200. So we've tripled the RPMs and less than doubled the amp draw. However, this thing's running on one leg. I'll shut it down for a minute. Why do I mean it's running on one leg? It is because it's not supposed to keep repeating when the thing is there, and I have to figure out from the code why it's doing that. When that's resolved, that distinction should be even more clear, and hopefully it will draw even less. But what did I just say? I just said, I think 30 milliamps and 1200 RPMs. So we're spinning at 1200 RPMs with 30 milliamps. This is 12 volts. So 360 milliwatts. So a good bit less than half a watt, between a quarter and a half a watt. We're spinning this at 1200 RPMs. So even with the screw up, that's not too shabby. Now, because this small coil works, even before I correct that, we can go to a higher induction, higher resistance coil, and we're going to do even better here as compared to RPMs, unless I'm mistaken. So let's do that and wrap this one up. So here's the slower, thinner wire, higher inductance, greater resistance, red coil. And if we look at small red coil, yes, small red coil, the half of the resonant frequency is 2.5 milliseconds. So that's what you want. So let's put it at 5 milliseconds and see what it does, and then put it at 2.5. Again, the code is all kerflooey, and it shouldn't make that and be drawing amperage, but I'm still seeing a distinction between in resonance and out of resonance. So I'm just going to finish with this and then figure out what's screwed up with the code. And once you get rid of that where it keeps drawing amps when it shouldn't be, this is going to be even better. Alright, so here we're running it with this coil, and there's the tragic problem of that. That should not occur. There's a problem with the code. But you can still, and it likes to switch directions, you can still see that there's a difference between when you're in and out of resonance. The other thing I'll just demonstrate real quick is that those swinging magnets, they get rectified to this coil and they get sent back to source. And if you think I'm lying, what I'm going to do is I'm going to take this and I'm going to push it in. I'm going to push it in right now. Right. Wait a minute. Let's get it here. You have to be at the right place too, the right angle. Oh fuck! It's going the other way now. I'm French. No, I'm not. I just like to curse that way. All right, I'm gonna give up on that for the moment. What I was going to show you is that when you have this in the right place, and this is, oh my gosh, I forgot I was on. And this is spinning. When you bring it in close, when you have it right, the amp draw will be, say, 20 milliamps. You bring it in real close, it'll go down momentarily to 10 milliamps, negative 10 milliamps. So, you know, if it's spinning at, say, 1,000 RPMs, you bring it in close and drawing, you know, 100 milliamps. You bring it in close, it'll go down to negative 10 milliamps. And then the rotational speed will drop from 1,000 to, say, 500. And then you'll go back up to, say, drawing 50 milliamps. So what it's documenting, those spinning magnets, depending on your positioning, and it's all about timing. I mentioned this in the last video. They are in fact getting rectified back to source, because otherwise, when you brought this in close, there wouldn't be a change. Let me see if I can at least show something. Yeah. And then it'll slow down and it'll go back to... So let me see if I can find a decent spot for this and see how this one compares with the other coil. And, you know, you'll see that go negative. It's kind of cool. So here we're drawing, and, you know, it's a pretty much steady state, 4.4 milliamps. And we're spinning at... Oh, darn it. Screwed that up. Is that right? That can't be right. Wow. So we're spinning at 475 RPMs and 4.4 milliamps. So that is quite better than we were doing before. And again, this isn't like shoving the coil in or whatever. I'm just saying that as you position this coil, you're getting rectification. So you're drawing 4.4 milliamps. 10, that's 12 times 4 is 48. So 50 milliwatts. So about what an LED is for 500 RPMs, 400 RPMs, whatever I said, 470 I think I said, RPMs, and 50 milliwatts.